Another way to calculate delta H is using enthalpy of formation, or the delta H of formation, which I will talk about in a second. You're going to need access to your textbook. So in the year that I'm recording this, this is the McGraw textbook online, which we haven't used that much. And so I'll show you when to have that out, so make sure you do. And then 4 highlighters would be handy, or any 4 colored writing tools, whatever, for one of the example problems we're going to go over. Okay, so enthalpy of formation. So delta HF. So the F subscript stands for formation, and so it's the standard of that. So we have that actual definition of it in terms of like, here's a definition, is what is stated on the screen. So change of enthalpy for a mole of a substance from its constituent elements in the most stable state, which is usually room temp, 1 atm, typically. Now, what the heck does that mean? So, think of the heat energy involved when you make something. So, let's say we're making H2O. You got your H's and your O's. And so those are its constituent elements, and then you're trying to make H2O. That's what it means. Okay, so whatever substance you have, it's made out of different elements, and so whatever those elements are, that's its constituents, and then you use some values from a table, and then bada bing, bada boom, you do math. Okay, so one thing is don't forget your diatomics. So one way of, again, memorizing it is this. You can use a mnemonic. The other way that I personally used when I was in AP Chem is this one, where, hey, look, on the PT, it makes a 7, and you just remember H because it's weird, and there's 7 of them in total. So however you want to memorize your diatomics, again, use whatever. So, whatever. And so one thing to know before I even show you any kind of ways of calculating this, delta H F for elements are always 0. Make sure you know this. And why do we need to know this? Again, I'll show you in a second. So make sure to know that, okay? And so the reason why they are 0 is because they naturally occur in nature. In nature, we have oxygen. Cool. We have lithium. Cool. So if it's an element, it's just straight up 0. And if you're like, huh? Don't worry, I got you. One thing I haven't mentioned before that I straight up forgot to mention in a previous unit is when you're at room temp, which again is 25 degrees Celsius and 1 atmospheric pressure, what elements are gases versus liquids versus solids? This screenshot is from ptable.com. I highly recommend bookmarking it in case you need a periodic table handy online. So this table, you can set the temperature. So here I set it at 25 degrees Celsius. This is at 1 atmosphere. And so you can see on this PT, most of the table is solid. You can see the key right here based off the coloring. So you have this kind of grayish color for the symbol. It's solid. So solid, 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 and so on. So most of the table is solid. There are some gases you should know exist as gases at room temp, just intuitively. So first we have the noble gases. So see this purple? So all of these guys right here, from helium to radon, those are purple. We have number 118. We don't know much about that guy, so don't worry about him. But in general, noble gases are, well, as implied, gases. Then we have our diatomics, so NOF, Cl, and H. Those guys are gases. Br and I, you're not really going to deal with much, if at all, but in case you do need to deal with it at room temp, bromine is a liquid, as you can see right here. It's this coloring. And then iodine is this color, so it is a solid. You can see in this table again, most is solid. You don't really need to know that, but it's just, handy to know. Mercury exists as liquid at room temp. Very dangerous substance, but yeah. So make sure you know your gases, good to know for this section, good to know in general for this class. So we're going to go over an example for delta HF. So here is the reaction we're going to analyze. So notice we have a carbon by itself, it's an element by itself. We have O2, it's a diatomic element, still an element by itself, and we're forming CO2. So when I'm looking at a chart of references for that delta HF, I am only going to look for carbon dioxides. The delta HF for elements are 0, so I'm not going to worry about carbon. I'm not going to worry about O2. If I looked it up on a chart, it would just say it's 0 if it's even given in the chart in the first place. And so you would look up delta HF on a chart, and so that delta HF, we're keeping it 1 mole, and so you might need to do fractions. I'll show how in a sec. So here's an example of what happens if you need weird fractions for stuff. So when we're forming water, H2O, this is the balanced equation if I'm using just the constituent elements, right? So we're balancing it out. Great. But you want your product to be a mole of 1 when you're using delta HF stuff. So I'm going to divide every coefficient by 2, and so I end up getting this reaction here. I know that's really weird because we don't have coefficient, that are fractions, but for delta HF stuff, you need to make sure whatever you're trying to form is a mole of 1. And so when you are doing your turn, you're going to set it up exactly the same way as like this, but you want to make sure it's the coefficient of 1 for the product. So go ahead and write the chemical equations as if we were forming all of these from its constituent elements. So go ahead and pause the video real quick and then try it out. Ready? Here we go. So, you don't really need to know states of matter for this particular section, but just like how I talked about with the ptable.com screenshot, here's my states of matter based off that. So you could write it. You don't really need to know, though, for this particular thing, but I wrote it anyway. So, again, you have to make the product side equal 1 mole, and so that's why you have all these weird fractions. The way that I did these is I balanced it like I regularly balanced it, and then divided by whatever coefficient was at the product to make it 1. And so that's how I did these. The oxygen on the last one is 3/2. I was just too lazy to make it a fraction because I'm typing on Google Slides. So there you go. Okay, so we figured out what delta HF is. It's just some kind of substance, whether ionic or covalent, doesn't matter. And we are forming it using its constituents as we wrote down in the your turn and the previous example. And so now that we know what delta HF is, we can now calculate the enthalpy of reaction using those values for delta HF. And so on our constant equation sheet, we have the equation that I have arrowed in red. That is the one for 6.8 section. So in 6.7, I mentioned how this equation is very, very similar looking compared to the one you actually use in 6.7. So make sure you don't mess up. It is very easy, and I've seen it many, many times students mess this up. So let's go ahead and break down this particular equation. So as a reminder, this symbol is sigma, the Greek letter symbol. It's the uppercase Greek letter for sigma, and it means summation. So you're adding all the delta HF values for the products, and you're subtracting the reactants, okay? And then your delta H with the little degree sign, that's standard state. Standard state, again, is 1 atmosphere and at room temp. And then the delta HF is, again, heat of formation. And then since it has the degree symbol, it's the standard state. And then reaction, it's the same thing if I wrote both. Whatever. So, this is what we're using for 6.8. But as I said, again, 6.7, which was the last section, has that slightly different one, but it looks so close to this one. So please be careful. I've seen it too many times that students messed up. As of recording this video, we currently are using the McGraw textbook. So I'm going to record another video showing how to get here. I have the general directions here, but I'm going to record a separate one that's going to be a private link because I might have to use a student account to show it rather than me, and it might have a student's name on it. So that's why I'm going to record it separately. And so try to get on this. If you can't, watch the other video before continuing this one. So pause the video, get on to the textbook, and then go to table A2.1. But if you can't get on here, watch the other video to get onto those first, and then come back. Okay, so you should have table A2.1 in front of you. You're using the delta HF side in order to find these values. Now, one note is I didn't double check if the values from the old textbook matches the same values as the new ones. So if the chart is slightly different in value, different references, different numbers, but it'll be about the same. So that goes forward with this example as well as the your turn. Okay, so here is the reaction we're going to be doing. So there it is. Yay. It should be a familiar reaction to ya from biology or living earth, whatever class you took. But anyway, here's our reaction. And so let's say we're trying to find the enthalpy of this reaction. And we have the delta HF values given to us on a chart. So just like for the previous section, if you need the delta HF for values for an MCQ or FRQ, they will give you a smaller version of the chart. I just gave you the whole appendix to look at just to find stuff. But again, they'll just give you the values you need plus a little bit of extra. Now, sometimes they don't put the element equaling 0. You have to know that by heart, but sometimes they do, sometimes they don't. I've seen it both, so keep that in mind. Okay, so in that reaction, we need to look up the delta HF for every single substance that's there. And so be careful about the phases that are listed in this problem because the phases matter. If you have a different phase, you will have a different value. That's why some of these substances on that chart are going to be listed multiple times because of being a solid, liquid, gas, or dissolved in water. So that's why be very mindful of that. Okay, so here is the equation that was given earlier. And so I'm going to look at our example reaction and determine what goes where. So again, elements are 0. You do not need to look them up. So what are we even doing? Okay, so in this thing, we have to look up for the product side. We have to look up CO2 as a gas and H2O as a liquid. Okay, so those are our products. In our reactants, we have this guy, sugar. You don't need to look up O2 because, again, O2 is going to be 0 because elements are 0 because they're naturally occurring. So make sure that you know that. I've already said this hella times. So cool, cool. In this example, this is where the highlighters come into play. So if you have highlighters or any other colored writing tools, that'd be great. So I will use them again in this example. All right, so we have our products. So I look up CO2. So CO2's value is this as a gas from the delta HF charts. And so I have 6 moles because that is the coefficient on CO2. I just multiply those bad boys out. I get that many kilojoules. I do the same thing for water. So I have 6 moles of water, again, from the balanced equation. I look up the value for the delta HF, and then I get that. And when I add those babies up, I got negative 4077 kilojoules. So I do the same thing for the reactants. Again, O2 is 0 because it's an element by itself. Again, the charts on an MCQ or an FRQ sometimes will show that, sometimes they won't. So make sure you know. So I have this right here. I have 1 mole of it, so those cancel out. And then I have that value is just that. So my sum for the reactant side is just going to be negative 1275. So that is the beginning of this problem. The next thing to do is literally plugging it into this equation up here. So I have my product side. So my products was negative 4077. My reactants, again, is right here, negative 1275. And so I input those values. Be careful about negative signs. It's very easy to mess up. And then I just add them up. And then I get my moles of reaction for the heat energy in kilojoules. And that is literally it. This problem got a negative answer, so that means this is an exothermic reaction. Okay, so again, you should have the appendix charts in front of you. You're going to do the delta H reaction for that equation up there by looking up values, skipping the ones you don't need to do, and so on. You also want to make sure it's a balanced equation. It's always good to double check that before starting. Usually it's given to you balanced, but if it's not, double check. So go ahead, pause the video and try it yourself. Ready? Here we go. So I looked up the values. I just put them underneath. Again, this is all kilojoules per mole from the chart. Everything is 1 mole because it is a balanced equation, so I didn't need to do any multiplying at all. And so I'm going to go ahead and put products and then reactants. So I have my products over here, I have my reactants over here. I input the values, make sure you do the algebra good, and then there we go. It is a negative value, so it's an exothermic reaction. It didn't ask for that, but again, as a reminder, delta H negative is exothermic. And then, that's it for the section. So you should be able to look on those charts or a truncated version for any practice problems. Again, it is the equation that is on the constant equation sheet. Do not confuse it with the previous section because, again, very easy to confuse. All right, bye.